Welcome to the Deep Dive. If you're gearing up for your welding inspector exams, especially CSWIP 3.1, you are definitely in the right place. Today, we're kicking off a series designed just for that, the CSWIP 3.1 exam prep series. Our goal, to help you really get the concepts behind those tricky multiple-choice questions. Not just memorizing, but understanding. We've got some typical exam-style questions lined up. We'll go through them, look at the options, and really unpack the why behind the correct answer. Ready to jump in?
Absolutely. It's all about connecting the dots, isn't it? Understanding the principles makes tackling those questions much easier. Let's do it.
Okay, first scenario. Let's talk MIG welding. It's pretty well known for being susceptible to lack of fusion, a really common issue. So thinking like an inspector, what's the primary cause here? Is it A, poor maintenance of the equipment, B, incorrect settings, C, poor interrun cleaning, or D, all of the above? What do you think?
Right. Well, this is a classic example where it's often not just one single thing. The answer here is indeed all of the above.
Ah, okay. So it's a combination.
Exactly. Think about it. Poor maintenance. Maybe you've got a worn liner in the torch, or the contact tip is knackered. That can cause, erratic wire feeding, an unstable arc.
Which means not enough heat.
Precisely. Not enough heat input means you just don't melt the base material properly. No fusion.
Okay, makes sense. And incorrect settings.
Same sort of problem, different cause. Maybe the voltage is set too low, or the wire feed speed is way too high for the joint. Again, you're just not putting enough energy into the weld pool. The weld might just kind of sit on top instead of fusing in.
Gotcha. And the cleaning. Poor inner run cleaning.
Yeah, this one's crucial too. If you leave slag or maybe rust or, any gunk between the weld passes, it acts like a physical barrier. The molten metal literally can't fuse with the layer underneath or the base plate.
So it really highlights it for an inspector. You can't just look at one thing in isolation.
You absolutely can't. A defect like lack of fusion often points back to a breakdown somewhere in the process control. Could be the machine, the settings, the prep.
Or all three. It's like detective work.
It really is. You need that holistic view.
Okay, good start. Let's switch gears a bit. From the process to the consumables themselves. Electrode handling. We're looking at the E6010 Electrode AWS A5.1 classification.
Yeah.
What's the correct handling procedure for this specific type? Do you, A, bake it for 1 hour, B, say baking is not required, C, bake for 1 hour at 100 Celsius, then store it at 70 Celsius, or D, bake it for 1 hour at 180 Celsius?
The E6010. This is a really important one to understand because it's different from many others. The correct answer is B, baking not required.
Not required. Why is that? I thought most rods needed baking.
Well, many do, especially low hydrogen types, but E6010s are different. They're cellulosic electrodes. Their coating is designed to have moisture, which produces hydrogen in the arc.
Hydrogen? Isn't that usually bad? Causes cracking.
In many cases, yes. But for cellulosic rods like the E6010, that hydrogen is actually beneficial. It gives it that forceful digging arc and deep penetration they're known for. Baking them would actually drive off that necessary moisture and degrade their performance. You'd lose the very characteristics that make them useful.
Huh. So baking actually hurts them.
Exactly. Unlike, say, a 7018 low hydrogen rod where you must bake it to remove moisture and prevent hydrogen cracking, for a 6010 you use it as is, maybe straight from a sealed can or just from dry storage.
That's a crucial distinction. So knowing the type of electrode and its specific chemistry is key. It's not just about keeping things dry.
Absolutely. You need to know why you're doing something, or in this case, why you're not doing something.
Right. Okay, sticking with electrodes, let's think about MMA, or shielded metal arc welding. Say you're inspecting and you see electrodes, but their coatings are damaged, chipped, cracked, that sort of thing. What specific defect are you most likely going to expect in welds made with those dodgy electrodes? Would it be A, porosity.B, undercut.C, excessive penetration, or D, excessive bead height?
Okay, so damaged coatings. The main issue you'll run into here, the most direct consequence, is a porosity.
Porosity. Why is that?
Well, think about what the coating, the flux, actually does. It has several jobs, but a primary one is creating a shielding gas. This gas protects the molten weld pool from the surrounding air, specifically oxygen and nitrogen.
Like a protective bubble.
Exactly. Now, if that coating is damaged, chipped off, or cracked, it can't produce that consistent shield. Gaps appear in the protection. Oxygen and nitrogen from the atmosphere rush into the molten metal.
And get trapped when it freezes?
Precisely. They form little gas bubbles, voids within the solidified weld. That's porosity.
So while other things might go wrong with bad technique, the damaged coating directly leads to that atmospheric contamination.
That's the most direct link, yes. You lose the shield, you invite porosity, it compromises the weld from the inside out.
Shows how important even just visually checking your consumables is before starting work. A small chip can cause a big hidden problem.
Definitely. Good inspection starts before the arc is even struck. Check those consumables.
Okay, let's change process again. Moving over to TIG welding. Imagine you're TIG welding, but the material is non-deoxidized steel. What specific defect should you be particularly wary of? Is it A, undercut, B, porosity, C, tungsten inclusions, or D, linear misalignment?
Right, TIG welding, non-deoxidized steel. This highlights the interaction between the process and the material chemistry. The defect you'd most expect is B, porosity.
Porosity again, but TIG has excellent shielding gas coverage, doesn't it?
It does externally. The argon shield is very effective at keeping the atmosphere out. But the problem here comes from within the steel itself. Non-deoxidized steels have, well, higher levels of oxygen bound up in them, often as iron oxides.
Okay.
When you hit that steel with the intense heat of the TIG arc, that oxygen can react with the carbon that's also naturally present in the steel. This reaction forms carbon monoxide gas, CO.
Ah, so gas is being created right there in the molten pool.
Exactly. And if that gas bubble doesn't manage to escape before the weld freezes, which happens quite quickly with TIG, it gets trapped, resulting in porosity.
Even with perfect external shielding?
Even with perfect external shielding, it's a material issue. While you can get tungsten inclusions from bad technique in TIG or undercut, the porosity risk is inherent when welding non-deoxidized steel with this process due to its chemistry.
That really drives home the point that an inspector needs to know their materials just as well as the welding processes.
Yeah.
You need to anticipate these kinds of interactions.
Absolutely. Material certification, understanding the specs, it's all part of the puzzle.
All right, final question for this deep dive. Let's talk power sources, specifically for MIG-MAG welding. What is the static output characteristic that's required for MIG-MAG? Are we looking for A, constant current, B, constant voltage, and C, constant polarity, or D, constant amperage?
This is fundamental to understanding how MIG-MAG actually works. The correct answer is B, constant voltage, or CV.
Constant voltage. Why is it the standard for MIG-MAG?
Because MIG-MAG relies on a self-regulating arc. A constant voltage power source is key to that. It keeps the voltage across the arc relatively stable.
How does that help regulate things?
Well, think about the arc length, the distance between the wire tip and the workpiece. If the welder moves the torch slightly closer, shortening the arc, the CV power source automatically increases the current. More current means the wire burns off faster, which naturally pushes the arc length back out.
Ah, okay. And if they pull away, making the arc longer?
The opposite happens. The current automatically decreases, the wire burns off slower, and the arc length shortens back to where it should be.
So it constantly self-corrects to maintain a stable arc and smooth wire feed.
Exactly. That stability is crucial for the continuous wire process of MIG-MAG. Processes like MMA or stick welding typically use constant current, or CC, where the current stays stable and the voltage varies with arc length.
It's a different philosophy matched to a different process.
Totally different. Understanding that CV is essential for MIG-MAG helps an inspector verify the setup is correct and diagnose problems if the arc is unstable. Is the machine set correctly? Is it functioning as a CV unit should?
Great stuff. So understanding the why behind the power source characteristic is another tool for the inspector.
Definitely. It connects equipment to process performance.
Wow. Okay, that was quite a run-through. We covered lack of fusion in MIG stemming from multiple issues.
Maintenance, settings, cleaning.
The specific handling of E6010's no baking required because of that cellulosic coating.
Right. The hydrogen is actually helpful there.
Then, damaged MMA coatings leading directly to porosity because the shield fails.
Yep. Atmospheric contamination.
TIG welding non-deoxidized steel causing porosity from internal gas generation.
From the oxygen and carbon reacting in the steel itself.
And finally, the need for constant voltage power sources to enable that self-regulating arc in MIG-MAG.
That's a good summary. It shows how interconnected everything is.
It really does. And hopefully for everyone listening and prepping for their CSWIP 3.1, breaking these down helps build that deeper understanding, not just rote learning.
Absolutely. These questions aren't just trivia. They're gateways to understanding the core principles of welding metallurgy, process control, quality assurance. The more you ask why and connect these ideas, the stronger your foundation becomes.
Couldn't agree more. We hope this deep dive gave you some valuable insights and maybe a few aha moments. Keep digging deeper, keep asking questions, and stay curious. Think about how these different defects or procedures might interact on a real job site. Until next time, happy inspecting.